Alright, hi y'all. Today we're going to be going over this EM Fall 2020 exam question 2, and this is a follow-up from a video before where I went over exam question 1 where it talked about Poynting vectors and real and imaginary power. Now this one's a little different. This one's we're going to go over plots and transmission lines, namely some maybe the bouncing plot or however y'all want to call it here. We're going to be looking for, what's it called? The voltage as a function. I should believe it's time and length. Let me check here. Yeah, voltage as a function of time. So let's get, I guess we just read through this problem, right? So let's cut the gibber. So a voltage source is applied at the left end of a transmission line as shown below. The plot of the generator voltage, Vg of t, is shown below. The pulse peak is V0 equal 9 volts. So let's label our graph here. So we know this V0, this is what, 9 volts. Okay, then it says, and the width of the pulse is 2 nanoseconds. Okay, good to know. We have this width is 2 nanoseconds. All right, and then it says plot the voltage Vt at a point halfway down the line. Z is L over 2. Okay, let's look for that on our circuit. So it says plot it point halfway down the line, Z is equal to L over 2. Well, this entire transmission line here, so from source to load, it is Z is equal to L. So Z equals L over 2 is something like right here. Z is equal to L over 2. I hope y'all can see that here. Now, if the voltage signal or any signal is traveling at a constant rate or constant velocity, then we can say that if this entire time is 4 nanoseconds given by this t here, what is half of the 4 nanoseconds? Well, that's 2 nanoseconds. So it takes 2 nanoseconds to get from source to L over 2. It takes 2 nanoseconds. I hope y'all can see this, where I'm coming from here. Okay, and then it takes another 2 nanoseconds to get to the load from the halfway point. So what we're going to be doing is we're plotting this voltage as a function of time and length, and we're going to be going over 10 nanoseconds. Okay, well, the first thing I like to do when solving these plots is plotting a different plot, essentially a different graph, but using only starting and ending values. I'll show you what I mean. Here, let's say we make this quick plot here, and again, this is time in nanoseconds for us, and it doesn't matter what you call this. All I'm trying to do is plot a actually, we can just get rid of this. Let's do a number line. It actually makes this way easier. So let's say this is starting. This is 0 nanoseconds. Okay, so it takes 2 nanoseconds to get to halfway, to the point halfway. So let's call this 2 nanoseconds. Okay, remember we're trying to find the voltage at the halfway point. If we know this voltage here is what we're applying, this waveform is going to show up on our scale. So this is the starting point. So start. What is the width of our signal? 2 nanoseconds. So now what it reads is you're starting at 2 nanoseconds. The distance from when it starts to when it ends will be 2 nanoseconds. So this is the width. Now it then stops at 2 nanoseconds plus 2 nanoseconds, 4 nanoseconds. So now this is stop. Okay. Now, how do we know when it starts up again? Let's think about this. The signal is going to be going from 0 to L over 2 in 2 nanoseconds. Then it's going to be going from 2 nanoseconds plus 2 nanoseconds to the load. That's the whole 4 nanoseconds. That's when our initial incident voltage will end. Now, how long does it take for the reflected wave to get back to halfway? It'll take a constant 2 nanoseconds. So what we're going to be doing is we'll call this dead time when no signal is being read by, in our case, we could think about it as a scope. No distance or no voltage is going to be read by the scope at L over 2 for 2 nanoseconds. So we can say this here is 2 nanoseconds. This is dead time. Nothing is being read. Now, once it passes that middle line, L over 2, it will be read. So 4 nanoseconds when this first one stops, plus 2 nanoseconds, the dead time is 6 nanoseconds. This is when the reflected will start. I hope y'all can understand this, how we this number line kind of thing. I'm just showing y'all a very skeleton basic idea so that we don't mess up any of the initial and ending times. Those are probably the most important thing, because the other ones you can just plug into an equation. Finding the amplitude, that's very easy. You plug into an equation, you solve it. But this is where people will mess up. You have to know when your signal is being read by the scope and when it stops. So again, we start at 6 nanoseconds, and how long does the signal last? Well, it lasts the width, 2 nanoseconds, if we can see right here on the left. It takes 2 nanoseconds for it to go through the scope at L over 2. So again, this, let me do that in red this time. This is going to be what? 2 nanoseconds. Again, this is the width. So this will be 6 nanoseconds plus 2 nanoseconds. This is 8 nanoseconds. This is when the reflected wave stops. Now, if we wanted to keep going, we have up till, 10 nanoseconds? So let's see. So if we kept going, let's say we go to 10 nanoseconds, we'll even write this down here. What happens? Well, let's see, this was 2, oh shoot, my bad. This was 2, this was 4, this was 6, this is 8. What the? Oh, I'm dumb, sorry. 2, 4, 6, 8. Then we go back 2 seconds again because it gets reflected. This is the re-reflected. This is 10. So technically, this middle line, z is equal to L over 2, will not get the chance to read any more signals after or at 10 nanoseconds. So we do not include this last time. Again, this here will end up being dead time. So we have dead time in between our signals. This is the time it takes for the signal to go down the transmission line. This, of course, is the width of our signal. And these are the starts and stops of our incident and our reflected waves. Just to note, it only gets reflected when the characteristic impedance of the line does not equal the load resistance. All right, so now we've created this number line for time in nanoseconds. Now we need to figure out the amplitudes. And again, this one, I will show y'all how easy it is. You take an equation and you plug in the numbers you know. I'm pretty sure he's going to give you, almost 100% certain, he's going to be giving the equation for this. So don't worry too much about this. If he doesn't, just learn the equations. I mean, I don't know what else to say here. So V plus, which is our incident wave, which is the initial wave, is going to be equal to, and of course this is a function of position and time, is going to be equal to a Vg of t minus the position divided by the velocity in the dielectric. Dielectric is usually Teflon, which is, I think it's like root of 2.1 or something like that. Anyways, well, what is this A? What the heck? Like, why are we using A here? Well, A is going to be equal to the characteristic impedance divided by Rg, the source resistance, plus Z naught. A lot of the times whenever we are dealing with generators, this is going to be, I guess you could call it the coil resistance. In generators, they have coils. I know this is true in three-phase. I'm not sure if this would be true in transmission lines, but they all have some sort of characteristic like a source resistance, a coil resistance. And that's really what we're trying to not get here, but that's what Rg is. So in our case here, ZO, the characteristic impedance, is 25 divided now by 50, which is our Rg, plus 25. What is that? That's 25 over 75. That's 1/3. Okay, cool. We have an equation, and we have our only unknown here. Well, what happened here? What is this? What is Z? Remember, Z is L over 2. This is what we're given. Z is equal to L over 2. So let's write that down. Z is equal to L over 2. So V plus the incident wave, Z, which we can replace as L over 2, as a function of time, is equal to 1/3 Vg. Okay, well, let's write down Vg. T minus L over 2 divided by CD. Now, we're not given any of the Teflon. If we're not told if it's Teflon, we're not told any of the permittivity, so we keep CD as that. Now, that's what we have. I mean, that's our incident wave. Now, this looks really weird. How are we supposed to plot this? This makes no sense. What is Vg? What is L over 2? What is CD? Well, remember how we solved for this time plot. I didn't do this for no reason. So what do we know about what do we know here? In signals and systems right now, I'm almost certain y'all know so far about time shifts. I mean, you should know this from calculus too. Time shifts here, minus. So we have a time graph here. A time shift of t minus, you're moving what? Right. So you're moving right. For the incident wave, we moved right how many nanoseconds? Well, to start, we moved right 2 nanoseconds. So that is what you're going to put here. This is equal to 2 nanoseconds, or the time that your incident wave starts. So wherever your incident wave starts is going to be the shift, the time shift of your incident wave equation, your voltage incident wave equation. This makes it very easy. If you do this, really all you're solving for is the A value here. I mean, it's so straightforward here. All right. And now, I guess another thing you could think about is what is Vg? Vg is going to be the voltage applied at the battery. So Vg of t, in our case, it's just a 9-volt peak. So really what we're looking at here is let Vg equal, what, 9 volts. Therefore, V plus is equal to 1 over 3 times 9 with a time shift of, what, 2 nanoseconds. So then this is equal to 3, which is 3 volts, your amplitude, t minus 2 nanoseconds for your incident wave. And this is the equation, oops, that should not be a gamma. This is your equation for the incident wave when you're drawing it. Now, we know we don't only have one wave because, as you can see here, this is one wave and this is the second wave. So we have two waves. We have an incident wave and we have a reflected wave. How are we going to find the reflected wave? Well, the reflected wave has to deal with, of course, our incident wave, but it comes back at a ratio or a fraction of our incident wave. Now that equation is going to be given by, here we have V minus, which is our reflected wave, as a function of, again, L over 2, in our case the distance, and time. Now this is where it differs. Where it differs is we have this new constant. We have this weird L, upside down L, and the load, you would call this load. So the reflection coefficient at the load times, again, A times Vg of t minus L over 2, which in our case would be Z, divided by the dielectric velocity, the velocity inside the dielectric. Okay, well, what is L? What is this weird L symbol? What is it going to be equal to? Well, we know this is going to be equal to the load resistance minus the characteristic impedance divided by the load resistance plus this characteristic impedance. And for us, RL is what? 50 ohms, and Z naught is 25 ohms. So we have 50 minus 25 divided by 50 plus 25. This is looking very similar. This is 25 over 75. Again, 1/3. So in perspective, in like a general way to think about this, this is saying that the reflected wave will come back 1/3 less than the incident wave. Now, does that make sense? If we have this reflection coefficient at the load being 1/3, and we're multiplying it to, this is essentially in red, this in red is our V plus. So it won't be exactly V plus because our time shift is different, but for the amplitude, I guess you could think about, is, let me rewrite this. V minus, the amplitude of V minus is equal to this coefficient times the amplitude of our V plus. What was our amplitude of V plus? 3. So we do 1/3 times 3. So our amplitude for our V minus is 1 volt. And I'll show y'all here how the math works out. So V minus of L over 2 T is going to be equal to what? 1/3 times A, 1/3. A does not change, by the way. A will stay the same. And our reflection coefficient at the load will stay the same. Eventually, what you're going to see is also this thing called the reflection coefficient at the source, which is denoted by G. And I know y'all seen this, but that's what this is, and you'll see it, but it will not change. Now we do VG. What was VG? Well, VG was 9 volts. That's our V naught. That's our amplitude of our regular wave, or what our voltage generator gives us. So 9 times T minus. Now, we do not have to do any math here. We've done all the math up on this number line. What are we looking at? We're looking at the reflected wave. The reflected wave is our second wave. When does it start? The reflected wave starts at what? 6 nanoseconds. So that's what we're going to write. 6 nanoseconds. Now, just like we had said before, 1/3 times 1/3 is 1/9. Times 9 is 1. Okay, so 1 times T minus 6 nanoseconds is our equation for our incident wave as a function of distance and time. So we've created our two equations. I hope y'all can see how useful creating this is, just because it gives you a basic skeleton layout of how you're going to be creating your plot. So now, let's create this. We've created the equations here. Now let's create the plot. So we'll make this pretty quick. Once you know how to do this, it goes by relatively fast. Usually he gives us graphing paper, so you don't have to worry about plotting like this. You just plot the values. So we'll say this is 1 volt, this is 5 volts, and this is 3 volts. And we have time in nanoseconds. What are the important times? Well, let's look at our time graph. 2 is important, 4 is important, 6 is important, and 8 is important. So we start with 0, whatever. We get 2 nanoseconds, we get 4 nanoseconds, 6 nanoseconds, and 8 nanoseconds. And of course, we go up to 10, so we write out 10 nanoseconds. So here, where do we start? We start at 2 nanoseconds. What is the amplitude? Well, the amplitude is 3 volts. And we're using a triangular, we keep this shape when we draw these plots. So if you have a sawtooth, you would write a sawtooth. If you have a triangle like this one, you would write triangle. If you have a square pulse, you would use a square pulse. The shape does not change. So let's start drawing this. We have a width of 2, and we go up to 3 volts. So the midpoint should be at 3 volts, and we can draw out here. And there we go, we have our first graph, or our first little plot. Now, again, this is the start, and this is the end. S and E I'll write, and this in between here is the width. Now going back to our timeline here, we start at 6 now. So we start at 6, and we end at 8. And again, this is the width, 2 nanoseconds. Okay, we have to write another triangular pulse. And what is the amplitude of our reflected wave? Oh, it's 1 volt. And again, you see here, we start at 6. Okay, well now we know this is 1 volt, so we go here. And we're done. This is our answer here. Now, this wasn't too hard. This was one of the easier questions. But it is still something we have to learn. If you follow, you don't have to. I'm not saying you have to. I'm saying at the beginning, when you're doing these, if you do this timeline, it makes things a whole lot easier when you're trying to picture what your plot is going to be. Because if you try and do everything at once, it's going to be a little difficult. Now, of course, you could just go from circuit to plot, or circuit to equations, and you would get the same answer. It would work. But just be very careful with how you take these times. And I mean, that's going to be pretty much it for this question too. I'll actually work on question 3 right now and make sure to get it uploaded. But I hope y'all understood here, and if you had any questions, please let me know. But yeah, thanks for watching, y'all.